Good morning, sir.
Hey, Reina, how are you?
I'm fine. It is
So
good morning here. For
this
you,
is
it is night.
it's nighttime here, yeah.
Yes.
So I thought that it was at 9 o'clock.
Oh,
So I didn't check it went to my junk folder. That's what happened. The flyer you sent me, it went to the junk folder.
spam. Okay.
Okay.
I have
Yeah,
sent
that's
it to the
okay.
WhatsApp also.
Yeah. WhatsApp. That flyer, I didn't see that flyer. Maybe
No,
you sent it to Linda.
the link, today's link, I sent it last night. Just in the evening.
Yeah. So I hope there are enough people, right? I think there is some storm or something in
Yes,
Kerala right now.
there is a weather forecast today.
Okay.
So we don't know how it will be going. We hope
Uh-huh.
for the good.
Yeah, hopefully it will be all right.
Yes.
So
We'll be starting in within a few minutes.
yeah. It's all students or is it
No, it is of faculty, researchers, all a mixed community.
okay. Yeah. Yeah, let me try to share my screen. You can see my screen, right?
Yes.
Okay.
Good morning, all. Welcome to the today's session, CheMistery 2K20 Session 4. Today we have a prominent assistant professor and researcher Dr. Jane Thomas from University of Central Florida, USA. Today's talk will be on nanotechnology in energy harvesting and storing devices. The CheMistery 2K20 was jointly organized by Department of Chemistry and IQAC, Marthama College, Changatara, in association with Kerala State Higher Education Council. About the lecturer, Dr. Jane Thomas, he is currently a professor of nanotechnology, engineering, and photonics at the University of Central Florida. He earned his PhD in chemistry and material science from Kochi University of Science and Technology. He was awarded the Dr. K.S. Krishnan Fellowship by the Department of Atomic Energy, and he was offered a research scientist position in the College of Optical Sciences at the University of Arizona in the year 2001 and promoted to a research faculty in 2005. Later, he moved to University of Central Florida in 2011 and currently directs the Nano Energy Photonics Research Labs. He has published more than 130 scientific publications, including multiple papers in prestigious journals like Nature, Science Advances, Energy and Environmental Sciences, Advanced Material, etc. Also, he got many national and international media, including Reuters, Nature News, National Geography magazine, etc. That he is a recipient of the R&D 100 Award in 2015. He is also a recipient of National Science Foundation's prestigious Career Award in 2014. With this brief introduction, I welcome Dr. Jane Thomas. Similarly, I would like to welcome our principal, Dr. Raina Thomas, to this function. I also welcome the participants from various areas, students, lecturers, and young researchers to this function again. Raina, please.
Okay, good morning to all, and thank you for inviting me. It is my privilege to give you this talk, and I would especially thank Professor Raina Thomas for inviting me to give this talk. I'm very happy to give it to you guys because you are young scientists. Hopefully, you can get inspired by some of the things we are doing. So, thank you for introducing me. Dr. George TM. I assume his name is Dr. George TM. So thanks for your kind invitation and also kind introduction. And let me share my screen and
Yes.
yeah, you can see it, right?
Yes.
Okay, so I am going to talk about nanotechnology in energy harvesting and storing devices. It's a fascinating field, as I am going to mention what all things you can do with this nanotechnology in energy storage, harvesting, and storage. I am currently a professor at Nanoscience Technology Center and also with the joint appointments in College of Engineering and Computer Science and the College of Optics and Photonics at University of Central Florida. And, this is our material science and engineering department. We have about 23 faculty with a number of joint faculty, professors, associate professors, and assistant professors, and scientists, postdocs, and PhD students. And we have a graduate program as well as undergraduate program. Here in general, graduate program means PhD and masters. That's what you call there. Here it is the graduate program, but in India it's basically a master's and a PhD. And we have also a BS, there is no BTech degree here, it's all BS mostly, and the BS in material science and all other engineering branches. And that's what we have here. So we have a number of faculty, we have a lot of facility here, clean rooms, and so many other things. And also I have a joint appointment. I have an appointment with the College of Optics and Photonics. And that optics and photonics is a very fascinating field. As you might know, the laser and light is used almost everywhere for communication, and all the sensing, and just so many other applications are there. Also, our College of Optics is also very famous, and previously I worked at College of Optical Sciences, which is also a very famous center, and now it is a college in the world, and these colleges are the top 5 colleges in the world itself for these optics and photonics. And we have a number of career opportunities here, those who are interested in applying here for a graduate or an undergraduate program. We have a number of companies like Lockheed Martin, which is a defense contractor, very, very big companies. They make helicopters and aeroplane parts and all those things. Siemens, that is also another very big company in Orlando. We are located in Orlando, Florida. Orlando, you may be familiar, maybe because of the Disney World. All the Disney World, the world attractions are in Orlando. This is one of the top, maybe top 5 tourist destinations in the world. So all the Disney and Universal Studios, Disney and all those things are in Orlando, but our university and all other facilities are on the other side of that attractions. And Mitsubishi Power Systems as well as NASA. You might have heard about Kennedy Space Center. Kennedy Space Center is very close from here, only 40 miles from here, from Orlando. So we work with NASA and Kennedy Space Center for many things. Many faculty have collaboration with NASA and the Kennedy Space Center. And this is my group, my grad students, previous and current students who contributed to this work, what I am going to talk today, and postdocs and various undergraduate students, as well as funding here. All this research and everything is funded by different funding agencies, not like there were government funds, all those things. Here, faculty brings funding, and then the students are typically supported by the faculty for doing research for their fellowships and all those things. So this is where I got my money for doing the research, what I am going to show you. And the Florida High Tech, then the NASA and Space Grant Consortium, National Science Foundation, Air Force Research Lab, as well as Department of Navy, and some funding from University of Central Florida. So these are my group members a few years ago, I think at least 1 to 2 years ago. Unfortunately, this is the most recent picture I have for quite some time. Basically, it's not that easy to bring all these guys together to take a picture. So that was my group. And now this is what I am, my group. This is the research focus of my group. As you have seen from my affiliation, I have appointments with the College of Engineering as well as the College of Optics. I work on many of these things which are related to engineering and material science, which is supercapacitors, wearable devices, perovskite solar cells, and integrated energy devices. And this is the work I am going to talk today. But at the same time, I have another work, another section of the work, which is on optics and photonics, basically optoelectronic synapses, holographic 3-dimensional displays, optical and photoacoustic C-scan, optoelectronic synapses, and organic electrochemical transistors. And these are some of the papers we publish about these things. Optics field, that is ACS applied material. This very recently published a paper on sensors, on optical sensors and detectors. And this is the paper we published previously in Nature, two papers in Nature about the holographic three-dimensional displays. And this is the reason why I was hired in United States, basically to develop this type of materials, organic polymeric material or organic semiconductors. And here it is the acoustic C-scan, another technique to measure nonlinear optical properties. So just one slide about this optical work we do. The photonics and optics is a very fascinating field. Now we work on this neural network, and these are basically the neurons. You know that your intelligence comes from these neurons, how they are connected and how it compute things. So there is a field called the neuromorphic computing, which is coming up very quickly, and this is going to be, we believe that new devices will be developed in this direction in another 10 to 15 years or so. The difference in this case is these type of computers, it can simultaneously process as well as store information like humans. So if you think about it, humans, we do these two things together. So we process it, we can process the information data, and we can store the information at the same time in the neurons. So we make this type of synapses for those type of applications, the data storage and those things. And we recently developed one device, a device which can process and store information similar to optical synapses. Synapses are the connection, that is connection between the different neurons. And we have billions of these neurons in our brain, and that's how the computation is done in our brain. It's a very fascinating, but we do not know completely, or we know only the tip of the iceberg how it works. So we published that paper, and it was the cover page of this prestigious journal, Science Advances. Is an online journal from Science. And there was also a report in Nature Electronics that's about this type of about what we have developed. And very recently, we have published. This is just published online, and this has been. I just heard today that this paper has been selected as the cover page of this advanced electronic material. It's for making this artificial retina type devices. We know this retina, again, artificial in humans, it can not only see, it can process information at the same time, these type of devices. So that's about the work we are doing in the optics direction. But today what I'm going to talk about is mostly the wearable devices, and the energy harvesting and storing devices, the fundamentals of supercapacitors. And I will introduce to you the energy transmitting and storing cables, perovskite solar cells, and some of the integrated devices here. So introduction to wearable devices. You might have seen many of these things, at least one of the wearable devices you carry all the time, one of the wearable devices, that is your cell phone. But the outlook for the wearable is something similar to here, what you can see. Okay, here, if you look at this person, he has so many things, like, there can be prosthetic skin. Okay, and there can be prosthetic eyes. I just talked about that artificial retina and such type of things. And ECOG and EEG, those type of electrode-based devices which can measure extremely small electrical signals from your brain. Okay, it is going to be nanoamps, and that level of electrical signals, those devices can measure those things. And optogenetics, that is basically how the retina, ganglions and those type of photoreceptors, that is the information is passed from the photoreceptors to the ganglions and so on, and how this can be processed within your brain as well as in the retina. Retina is also a part of the central neural system. So that is the optogenetics, the science that deals with those type of optics, that is the light and how that is processed within the brain, that is the optogenetics. So we make some of these optical devices, optoelectronic devices, but also we develop these energy harvesting and storing devices. For example, for all these devices to work, it needs energy. So how you can give this type of energy? There should be flexible and bendable devices which needs to be attached onto the body. So for example, here in this case, this patch, okay, it can measure your ECG. Okay, you just need to put it on your body, and this small stretch of this patch can measure your ECG. So the idea is you don't need to go to a hospital and stay there for many days or so. You can have these patches on your body and you can do your daily work. Okay, you can go to your work, and these type of devices, it can measure your ECG, how your heart works and everything, all those things. And the information can be passed on to a remote devices or a wearable devices itself. Okay, wearable home rehabilitation and such remote healthcare or somewhere, or it can be passed on to your cell phone. For example, your iPhone has many of these options to measure your ECG and all those things, the most advanced iPhone. So iPhone 12 has an option to do some of these things. So the whole idea is these type of wearables can work like a check engine. For example, your car, once you are low in your fuel, okay, your petrol, it can show you a light. Okay, it's time for you to go to the petrol station for pumping petrol. Likewise, here these type of wearable devices can warn you, okay, now there is something wrong on your body. Go to your doctor and do a thorough checkup. And that is the reason why the NIH, the American National Institute of Health, they have a goal of developing precision medicine. That means, it is to be, it is prepared for each and every person. It is not like a medicine for a group of people or certain type of blood group or anything like that. Once you get data from each and every one, it is a personalized medicine. Okay, this is just made for you. So that is the whole idea. Now, moving from there, now you can see, look at this one. Okay, let me show this. What is this video about? This is a school bus from where the kids are getting down, and a truck is coming from the other side, from the other direction, and these kids, school kids, they are crossing the road without looking whether there is any vehicle coming from the opposite side. But for an intelligent vehicle, okay, or a self-driving vehicle and such things, basically because of these sensors, I call it as also wearable for the vehicles. These, unlike humans, we cannot see our viewing cone is limited. Okay, our viewing angle is limited, but these machines can see, even if there is another vehicle in front. Okay, some of the most recent Tesla, the self-driving, semi-self-driving cars, it can see what is happening at least beyond four vehicles in front. So that is the key. So here in this video, you can see that these kids are crossing the road, but a truck is coming from the other side. Look at this one. So this truck was able to see it from the far. So it was slowing down, and it stopped at the right point, saving that those kids. So that's the reason why this type of devices, are so important. They can see things that humans cannot, basically because of the infrared, near infrared, and that type of radiations, the light that is coming from this type of vehicles. So coming back to this one, you have seen, now the electric vehicles are coming into picture, a lot of them here. There are a lot of companies are making these electric vehicles. Tesla is one of the pioneers in this field, making a number of electric vehicles. And this electric car, the Tesla Roadster, it is called a Roadster. It can go from 0 to 100 miles in less than 2 seconds. That acceleration is so fast. From 0 to 100 miles speed, 100 kilometers speed in 2 point, sorry, in 2.3, that is the most one, in 1.9 seconds. That is 0 to 60 miles in 1.9 seconds. So it needs a huge power in getting that speed from 0 to 100 0 to 60 miles, or 0 to 100 kilometers in 2 seconds time. And here there is the picture of another self-driving car from Mercedes. And all these things, they have this type of wearable devices. So you have you are very familiar with the batteries. Almost all of you guys carry batteries in your pocket because your cell phone has a lithium-ion battery there. But you haven't heard much about another type of energy storage device, which is called the supercapacitors. So I am going to talk about those supercapacitors today. So what is the difference between these two, batteries and supercapacitors? Batteries can provide a high energy density, a long discharge time, power density, inferior number of cycles, and slow power delivery. Whereas a supercapacitor, it is low energy density, discharge time is less, high power density, high durability, and high power delivery and intake. So you might not have followed any of these things, at least some of these things. What is the difference between this high energy density and high power density? So a simple example for that one is, you have your laptop. A laptop can last for maybe 6 to 9 hours time, because they all work on lithium ion batteries. So basically, because the energy density of lithium ion battery is very high. Whereas in the case of supercapacitors, typically the energy density is low, but the power density is high. So we just saw the car, okay, or the car which can go from 0 to 100 kilometers in 2 seconds. In order to go that quick, it needs a burst of energy, that is, a huge power is required. So these supercapacitors can provide that huge power. And once it reaches that speed, these batteries can take over that car for a stable energy. So that is the difference. This can give the energy provided by batteries can last longer, but the supercapacitors can provide a huge energy, a burst of energy, which means you have a high power density. So, but it can give a number of cycles. For example, your lithium-ion battery can last for maybe 2,000 or 2,500 to 3,000 charge discharge cycles. Whereas supercapacitors can go for, some of the supercapacitors can go for even millions of cycles. So nothing happens. So that is the reason why they are very reliable, and they have been used as in the emergency doors of A380 Airbus. They are very reliable because it can charge and discharge for so many times without much problem. So what is the difference between these different types of devices? There can be a few types. One is the double layer capacitor, another one is the pseudo capacitor, and the third one is the lithium ion battery. So I think most of you guys are chemistry people, so you may understand many of these things, and I am talking more chemistry in this talk, basically because it's conducted by chemistry department of your college. So here you can see that this is one electrode, this is another electrode, and the double layer capacitor is basically because you have the electrons coming here, for example, and there are ions on the other side. There is an electrostatic attraction between the negatively charged electrons here and the ions, and therefore the charges can be stored here. There is no chemical reaction taking place in this case, and the energy stored in this type of supercapacitors or double layer capacitors is basically because of the electrostatic attraction between the ions and the charges they are present on the electrode. And there is another type called pseudocapacitors. For example, you have a back electrode, and then you have some active materials here like manganese dioxide. And here in this case, energy is stored by a Faraday reaction, which means that there is a charge transfer between the electrode and the electrolyte. So you can see that it is for example, in this case, this is the manganese 4 ion, and when an electron comes to that one, this is the charging process, and that manganese 4 is converted to manganese 3, attaching one sodium. That the charge is compensated by this sodium storing one electron here. So your charge is stored here because of this Faraday reaction, and that is used for this pseudo capacitors. Here also, in this case, you have a huge surface area. Mostly this Faraday reaction take place on the surface of this electrode, this manganese dioxide. And in the case of lithium ion batteries, here you have, for example, graphitic layer. Okay, and here also it is the Faraday reaction. Okay, exchange of charges take place, like here in this case there is a exchange of charges, and the difference between this pseudo capacitor and lithium ion battery is here you have a bulk material, and the charges diffuse into, or the ions diffuse into, lithium ions diffuse into the bulk of this electrode. Okay, and this is, therefore this is a diffusion control. It has a much thicker electrode material. So the basic difference, you can see it now itself here in this case. Since you have that thickness, the electrons need to go into this bulk of the electrode, and this is diffusion control, so it takes time. Whereas in the case of pseudocapacitors, most of the charges are stored on the outside of the electrode. So since the charges are stored on the outside surface, they can be discharged very quickly too. So in the case of lithium ion battery, discharging take longer time, whereas in the case of pseudo capacitors, it takes much faster. So now it is clear to you, I hope, that in this case, in the case of lithium ion battery, you have a constant energy density or energy supply for a longer time, whereas for the pseudo capacitors, it is a burst of energy, and then the energy density, that is lower than lithium ion batteries. So that this is the difference. And now the question is, are you interested in replacing batteries with the supercapacitors? There are a few instances where the supercapacitors can completely replace the batteries, but the whole intention is not completely replacing batteries with the supercapacitors, but it can be in a supportive role in many cases. For example, if you have supercapacitors along with these batteries, the high power can be provided by supercapacitors, and a stable energy can be provided by the lithium ion batteries, so that lithium ion battery lifetime can be enhanced. That's the whole idea. But if you look at the the NASA's website, this NASA Glenn Research Center website, this is an astronaut drill. This is used in the International Space Station for the astronauts for to go for the spacewalk. If there is a repair necessary for the International Space Station, they take this type of drill, which is powered completely by supercapacitors. You can see these are supercapacitor packets, and they cannot take such a long time to charge it and then go outside and do all those things. That's the reason why they use these supercapacitor packets. Another example is the Kappa bus, which is in China. If you look at here, there is no overhead cables or anything that powers this electric tram or electric train. So basically, how it works is it stops at a bus station, and it can charge within a few minutes, 2 or 3 minutes, while the passengers are getting down. It gets charged completely because it uses only supercapacitors, and it gets charged so quickly. By the time the passengers get down, and then this can be completely charged, and it can run another 5 miles to the next station. But much more recently, back in 2000, this is September 2019 or so, Lamborghini, they released a car. You know that Lamborghini is a very expensive sports car, is a luxury car, a very expensive one. And this Lamborghini, this car runs on a booster engine, which runs entirely by supercapacitors. It uses a supercapacitor, it's a booster engine, and it can go from that high speed, very high speed, within few seconds, basically because of this supercapacitor run the booster engine. So that is another example where it is completely used. So this is just to show the limitation of lithium-ion batteries. And this is a recent accident happened in US. And here you can see this is an electric car. This is a Tesla car. And it is nothing wrong with the Tesla car. It was basically because the driver was intoxicated and he was driving 100 miles per hour on a inside road or somewhere, and it hit somewhere. And what happened is this one. If you look on your right, you can see these are all lithium-ion battery cells. So it has so many lithium-ion battery cells, and as a result of that collision, these batteries flew to the neighboring apartment, that is the flat here, okay, and each went through the window of that apartment, and some of them landed on the beds of people, and it caught fire. So that is the problem with the lithium-ion batteries. It can easily it can catch fire very quickly, these lithium-ion batteries. So that is a big disadvantage, and you might have heard some of the news there. So that is the reason why in supercapacitors we use aqueous electrolyte. One of the reasons, or the main reason why it catches fire, is basically because of the organic electrolyte used in lithium-ion batteries. There is a dendritic formation, and which makes the anode and cathode touch each other, and it catches fire. So Here you can see the taxonomy of supercapacitors, how they can be categorized and all those things, the different categories and all those things. And there is a asymmetric and symmetric supercapacitors. I don't want to go through all these things, but if you are interested, you can go through some of our papers where all these things are mentioned very clearly. Because of the time, I don't want to go through all these things, but there is another one about the asymmetric supercapacitors also, and I will explain in a moment what is an asymmetric supercapacitor. And there is also another very recent publication from my group about this the transition method dichalcogenide type 2D material supercapacitors. And this paper was selected as one of the top 5 cited papers in 2018. It was selected in 2019. So here is the reason why we are talking about asymmetric supercapacitors. If you look at the capacitance, this equation, you can see that the capacitance is equal to A into epsilon R into epsilon 0 over D. Okay, where A is the electrode surface area, and this is the dielectric constant epsilon R, and this is the vacuum dielectric constant, and D is the separation between the two electrodes. Okay, that is the capacitance. And if you look at the energy density, okay, here we are talking about energy density basically because if you can increase the energy density, that can be used for many applications like batteries too. So in order to increase that energy density, if you look at this one ED, that energy density is equal to half C into V square, where C is the capacitance, capacitance you can get from here. So V is the voltage, that is the voltage window you can use in these supercapacitors or these cells, electrochemical cells, the V. So so if you look at this one, if you can increase the voltage generated by your supercapacitors, your energy density can be substantially enhanced. So our intention is to increase this V. And also look at this capacitance. Capacitance is directly proportional to A, okay, which is the electrode surface area. Here comes the nanotechnology, the beauty of nanotechnology. How can you increase the surface area of electrodes? That is that is where the nanotechnology comes into picture. As you know, nanotechnology is the best technique to increase the surface area. You are making the things so small so that the surface area increases. And as you ask chemistry students, you might know this thing, as the surface area increases, the reactivity also increases, the reaction rate, because you have a number of atoms on the surface which are very active, so the reaction rate is going to be increased and so on. So but I am talking about here the capacitance. C is equal to A from this equation, and energy density is this one. Now I'm going to talk about how you can increase the electrode potential, this voltage. This is the working potential window. Here the E is equal to working potential window. So this is a little bit I don't know whether you completely follow the students. Especially I'm a little bit worried about the undergrad students, but if you can just focus on this one, you can at least follow to some extent. So E0 plus delta A plus delta B, so which is equal to, we can write this equation as E0 can be written as 1 by F. Okay, this is the F is the Faraday constant, omega B, this is omega beta minus omega alpha into Na. This is the E0. Okay, and E0 is the electrochemical potential window. Okay, E0 is the electrochemical potential window, plus delta A is the surface dipole potential of the anode or the positive electrode, and B is that of the negative electrode, delta B. Okay, so this is the surface potential, and these are the electrochemical potential of the positive and negative electrodes. So when you rearrange this equation, we can write it as 1 by 1 over f into omega beta into Na, okay, minus 1 by f into omega alpha Na, plus this is minus of delta A, and so on. So now we can write this as electrochemical potential. You might have heard about the electrochemical potential plus surface potential of the electrode 1 B minus electrochemical potential plus surface potential of electrode A. So in effect, we can write it as work function. This gives, that is the electrochemical potential of that material plus the surface potential gives you the work function of electrode 1. And here this gives you the work function of the electrode 2. Work function is a term commonly used in physics and in electronics. Okay, many of the electronics we use this work function. So what is work function? So if you look at here, you have, you know, these things. This is a semiconducting material. If you look at the picture on your right, you can see that there is a valence band maximum. That is here the valence band maximum, and this is the conduction band minimum. So you know that semiconductor has a forbidden band in between or the band gap between the valence band maximum and conduction band minimum. So the energy required to remove an electron from the top of your valence band to vacuum level. Okay, vacuum level is defined as the energy level at which, you know, the electron is completely free. That is the vacuum level, E vacuum level. So the energy required to remove an electron from the top of this valence band, that gives you the ionization energy. And what is electron affinity? Electron affinity is the energy released when you add an electron to the bottom of the conduction band. Okay, that is the electron affinity. And the work function is this one. Work function is the energy required to remove an electron from this Fermi energy level to the vacuum position. So what is this Fermi energy level? This Fermi energy level is nothing but the energy level at which there is a probability of finding the electron at absolute zero. Okay, you can see an electron up to this level at absolute zero. Above that Fermi level, you cannot see any electrons, but below this one, there is you can still, there is a probability of finding the electron. But above absolute zero, what the point is, the probability of finding the electron is half. Okay, that is the Fermi energy level. So the energy required to remove an electron from the Fermi energy level to this vacuum level is the work function. So that means your voltage window is determined by the work function difference between the two electrodes. That is the point. So that is, there can be two types of supercapacitors. One is the symmetric supercapacitor, and another one is the asymmetric supercapacitor. In the case of symmetric supercapacitors, the two electrodes are the same, are made up of the same material, and therefore this is the voltage you can get is the dissociation potential of the electrolyte you use. If you use water, that is the dissociation potential of water, which is about 1.23 volts. That is the dissociation potential of water when you use a symmetric supercapacitor. When you use an asymmetric supercapacitor, this is determined by, as I said, it's a work function of the material. If we can widen the work function of difference between the anode and the cathode, positive and the negative electrode, then you can get a much better voltage output from your electrode. And these are some of the materials which can be used for this purpose. Since I don't have much time, I am not going to talk about these things. Now here, this is a direction where you can modify the positive and negative electrode to get, this is artificially modifying the electrode surface to get a higher voltage window. And how you can measure this work function? This work function can be measured by a technique called the Kelvin probe force microscopy. It is a type of atomic force microscopy, and you can measure the work function of this material. And very recently, we published a paper how we can do this work function calculations, and that can be used to tweak the properties of supercapacitors. Now I am switching gears, and these are some of the research results we have developed, and these are some of the cables or the fibers that can conduct electricity as well as store electricity. So we have cables, these cables are made up of copper, and we have miles and miles and miles of this copper cable. So our idea was, why don't we transform some of these copper cables into energy storage devices too? This is done by nanotechnology. What we did is we took this copper cable, and we made some of the nanostructures on the surface, which is a very it's a simple procedure where when copper is heated to a higher temperature, you can see the formation of this copper oxide nano whisker formation on the surface. And then we made that into a supercapacitors, and it is wrapped with another filament with these type of nanostructures to make a supercapacitor. Now what we have done, you can see that with that heating, you can get this type of nano whiskers with a diameter of about 120 or 140 nanometer, but a length of 20 microns or 22 microns. So now you can imagine how much aspect ratio you have here. It's a huge aspect ratio, which means that you have a huge surface area, and you got the point, I believe. That means by increasing the surface area, you can store a lot of energy on these fibers. That's how we made these type of cables. And if you look out here, we made an inner cable, a separator, and an outer cable with this type of nanostructures. We wrapped them together and made it into the cable form. In this cable, the inner side can be used to transmit electricity, whereas the outside can be used to store energy. These are some of the very typical electrode performance evaluations, cyclic voltammetry, and such things, just to show that this is a very good storage device. So this is the performance of the cable supercapacitors, where you can see that this can be completely bendable, and still the performance is very good. And here, this is just to show the cycle life. Even after cycling up to 5,000 cycles, here it is 5,000, and you can see that it is the capacitance retention, or the energy retention, is almost 100% itself, which means that this is a very stable energy storage device, and it showed reasonably good energy harvesting and storing properties. So, and then we demonstrated dual functionality for this cable, that is the energy transmission and energy storage. That is the dual functionality we have demonstrated for this cable. And this is the first time someone has shown that a cable can be used for energy transmission as well as energy storage. So it was a big news. It was even the prestigious journal Nature. They published a 2-page report about these cables, so which can be used to transmit and store energy. Here just there is a video which shows you how this cable can be used to store energy. This is like any other cable lying around, and you see this is that blue colored one is the cable we developed. It is more or less similar size to the other cable, and this cable is connected to a fan. This is a reasonably big fan. Okay, it's not that a ceiling fan, but reasonably big fan. And now this is getting charged. This cable is getting charged from this charger, and now you can see in the video this is going to be disconnected, and this fan can run just from the energy stored in these cables. So that's what you can see. I hope you can see the video. Now they are disconnecting it. You see, now this fan is completely operated by this cable, energy coming from this cable. So what is the point? What is the point we are trying to make here? Okay, this is the cable, one of the first cables we developed. And if this is a circuit, okay, this is a circuit platform, or and IC, for example, and you have a number of this CAN type capacitors, and our intention is to replace this type of CAN type capacitors with this type of cables. So once you replace this type of CAN type capacitors with this type of cables, you can see how much real estate you can get from this one. Okay, this can make this IC much smaller than this one. You don't even need to run these cables through on the surface. You can just run these cables around this around this one, this substrate, this platform, and then you can save this much space. So it's a completely new concept, and a company called Capacitors Energy, they are trying to commercialize these cables right now. So this for this work we got numerous news coverage from all the major national and international news, including Reuters and Yahoo News and so many other news vendors. So here there is the newer direction for this one. Okay, here in this case we take some carbon fiber and convert that carbon fiber into storage device, and that can be used for many applications. So electrophoretic deposition of the material, and here you can see this is the carbon fiber, and in this case we grow graphene vertically on this carbon fibers. Okay, that is schematically shown on your right. And you can see all these graphene nanosheets vertically stacked, and here is the scanning electron microscope image of that vertically stacked graphene. Here you can see all the graphene vertically stacked, and the graphene is a 2D material, as you might know, and it has a huge surface area. It is a capacitive material, and therefore since it can be grown on this type of carbon fibers, it can be very beneficial in storing energy. And this is here, if you look at this plot, okay, this is just a representation how many cycles you can get from that electrode, a single electrode. We have cycled it for 100,000 cycles. Okay, and still it keeps about 100% of its capacitance, that is the energy storage capability. So that is the beauty of this type of materials. For example, if you make some of some materials using this type of carbon fibers, for example, the structural components of vehicles using this type of composites made from these carbon fibers, that will be very beneficial to make the electric vehicle. Instead of having, that's the reason why I showed one of the pictures of the lithium-ion batteries flying around in an accident. But if you make this carbon fibers into a composite and used as the structural material of cars or automobiles, then that can be very beneficial, basically because it's the structural component. At the same time, we use water as the electrolyte. We do not use any organic electrolyte. We use water as the electrolyte, and we do not use any other toxic material. These are all benign materials and environmental friendly materials, and this can be very beneficial. Currently, we are working on this type of materials, and we are collaborating with some companies to develop it into very useful materials right now. So I think I don't have much time left. I don't know how much time I can take. Can I take
Yeah,
another 10 minutes?
yeah, sir. You can take it 10, 15 minutes.
Okay, that's great. So if you look at the this plot, okay, this is from Department of Energy, United States Department of Energy. This is famously called the NREL chart, okay, where they chart, okay, this is the National Renewable Energy Lab. So NREL chart, here you can see all the different types of solar cell devices. Okay, now I am switching gear to solar cells. Okay, basically to demonstrate you one aspect. In the previous work in the type of in the cables, I have demonstrated. You need to know. You can see that it needs to be charged. Okay, especially if you consider some of the soldiers, okay, who are in the battlefield. It is extremely hard for them to go back and charge their wearable devices or whatever electronic devices all the time. And it is very hard to deliver power packets to these soldiers at remote locations. Many times it can be catastrophic. So that's the reason why we not only us, but many people are working in this field. Can we make some of the jackets and such things out of this energy harvesting and storing devices? So energy can be harvested from the sun. Anyway, they are in the open field, open sun. Energy is from the sun is free and it is plentiful. And can we store some of this energy into on your cloth itself, onto their jacket itself? That's the whole motivation for this work. So if you look at this chart, you can see some of the solar cell. This is just the solar cell, okay, the performance of the solar cell. And the crystalline silicon solar cell, the efficiency, you can see it is about 26.7, which is shown in the blue colored plots here. It's a crystalline, okay, highly crystalline silicon solar cell. Whereas the another one, this yellow colored this plot, okay, which is called the perovskite solar cells. Okay, this is the perovskite solar cell, this one. It started back in 2010, 2008, 2010, that period. And initial efficiency was even less than 10%. And within that 10 to 12 years itself, the conversion efficiency, solar conversion efficiency jumped from that 8% to about 25.2, very recently reported efficiency. So this is a very promising material, basically because these solar cells can be developed by solution processing, and it is made from earth abundant starting materials. So it's a very promising material. So what are they? What are these perovskite solar cells? So the generic formula for perovskite is AbX3. As chemists, you might know about this one. A is the cation, which is the methyl ammonium. This is a cation, A. And B is another cation, which is the lead. Okay, that is B. And X is a halogen. Okay, it can be bromine, iodine, or chlorine. And it has a cubic perovskite structure. As you can see here, the center molecule is a lead molecule, and this is A is methyl ammonium. There is another cation, and these are either iodine, chlorine, iodine, or bromine, or chlorine, mostly iodine or bromine. So the idea is you can make this type of solar cell, semi-transparent solar cell. That was one of the initial work we have done in this direction. But why these materials are so important and why they are attractive and what are their limitations? One is the small excitone binding energy. That is also a technical term. This binding energy, there, whenever you illuminate this type of materials, there is an excitone generation. That is, the electrons and holes are generated, and in the case of organic materials, they are bound together, and in the case of inorganic material, it is free carrier generation and so on. But in the perovskite, it is people, there is a controversy on that one, whether it is an excitone generation or a free carrier generation. But still people believe that the excitone is generated, but that excitone binding energy is very small, so that the electrons and holes, these electrons and holes are the charge carriers which can produce that current. So there is a small binding energy, so that these charges can be easily separated, and that can be used as the powering, that can be used to power the devices. So these perovskites have high absorption too. It can absorb a lot of light and high charge mobilities. And when you consider the thickness of these solar cells, the silicon solar cell you buy from market, the thickness is about 300 microns or so. Okay, 300 micrometer. That is the thickness of silicon solar cell. Whereas the thickness of perovskite solar cell, you require to convert the same amount of input light, that is the sunlight, is only 300 nanometer. You need only 300 to 350 nanometer compared to 300 microns in the case of silicon solar cell. So you need much smaller quantity, and also this perovskite can be made by just solution processing. Okay, whereas in the case of silicon, high temperature processing is required, which takes a lot of energy too. So this perovskite, it has a band gap of 1.1 to 2 electron volts and high absorption and all these things what I have mentioned so far. And there can be different types of solar cell. What is the one is the PIN and NIP. These are P type semiconductor, intrinsic perovskite layer, and then N type material, and so on. And that can be made into this type of solar cell. And if you are interested, you can look through some of these citations. If you want to know more about this configuration, is very interesting, and there can be a lot of things can be done on that one. This is one of the early work we have done in making a semi-transparent solar cell, a PCBM assisted method, which we have developed to make these semi-transparent solar cells from this perovskite. And you can see different layers there. And this perovskite solar cell, these are some of the characterizations we have done. Yield spectroscopy, energy low spectroscopy, which shows that this type of hybrid formation can be possible at the junction between PCBM and perovskite, and so on. So these are the photovoltaic characteristics, which shows that it is a good solar cell. Okay, all these IV curves and such things. And here is the device we developed. You can see that this developed, it is a you can see through this solar cell. That is the beauty of it. So what we are trying to achieve from here? You can make this type of solar cells, and you can put it on your window. Okay, instead of your window glasses, you can use this type of solar cells. It can screen the sunlight. At the same time, the screened sunlight can be used to generate electricity. So that is the whole idea behind this type of solar cells. So we have developed something like this solar cell has a average visible transmission 18%, That means this is like your sunglasses, okay, or what you call there are cooling glasses. And with the AVT, that average visible transmission for these sunglasses is 17%, but we have shown that our solar cell, semi-transparent solar cell can have 18% efficiency, sorry, 18% AVT, but still it can provide about 8 to 10% of solar conversion efficiency. That means 8 to 10% of charges can be generated from the solar radiation falling on that device. So as I said before, here on you are going to see the ribbons which can harvest and store energy at the same time. If you look at this one, okay, and here we tweak the energy levels of the material, we engineer the energy levels of the materials in such a way that the solar cell, here this part is the solar cell, is a perovskite solar cell, and on this part is a storage device, a supercapacitor. So here you can see this is a shared electrode, okay, and on that shared electrode the one side is completely made up of nanostructures. Okay, these are all nanostructures. It's a nanotubular type structure, and this is a shared electrode, which means that you can generate this electrons by illuminating this side of the device with the, or this is actually a ribbon, okay, this side is a ribbon, a copper ribbon, extremely thin ribbon, and then you illuminate on this side, the electrons are transferred to this shared electrode, and these electrons get stored in these nanostructures, okay, directly. The outside, the outer part is connected to the outer electrode of this storage device. So it is a highly integrated device, which means that the problem right now for your energy storage, energy harvesting and storing devices is that you have a solar farm and a grid where you can store some of this energy. These two are located at two different sites, okay. So the portability of this energy is very limited. So you need to in order to improve the portability of your devices, you need to integrate them so that people can easily carry around. So you don't need to worry about a separate storage device, you can have these two things together. So we have shown that by engineering all the energy levels, we can make a completely integrated device, and we published this work back in 2016 in this journal, Nature Communications, and this is how the method by which we develop these things. The first the solar cell, and then here is the supercapacitor part, or the nanotubular structures, okay, for the energy storage. And this is the performance of that supercapacitor, the energy storage capacity, and all those things. So here, this is the assembly of symmetric supercapacitor. That is what is shown here. There is a video, but I'll show you another video coming up. This is how we integrate these two devices together, and this is a thin film, or that ribbon of that integrated device. And this is a penny here, that is one penny here is this is just to show that this is extremely small in size. So this is the integrated solar cell performance, and compared to a standalone device, you can see that the integrated ribbon, it shows the same performance as a standalone device. And if you look at here we are showing that, okay, on this side, these ribbons are charged by a solar simulator. A solar simulator simulates the sunlight exactly like the sunlight coming from light coming from sun. Okay, you are illuminating this device with the sunlight here, and now the energy is stored here. you turn off that solar simulator. Now you are discharging the energy stored. You turn off the solar simulator, there is no light, but still the energy is stored in the device, and now you are discharging it at different currents. Okay, 1 milliampere, 2 milliampere, and so on. And here it is shown, for example, if you want to make it into a wearable device, it needs to be flexible and bendable. So we bend it at different bending angles and demonstrate that it can still keep all its performance. High performance can be, it can still provide a high performance. So then what we did is we weave these ribbons, into a cloth itself. Okay, here is a textile, a small piece of cloth we made. We bought a loom and learned how to weave it, and we weaved a small piece of cloth with these type of filaments in between. This is a very crude one, but still to demonstrate in proof of principle, the proof of principle where we can make this type of fabric, that is done here. And here is that fabric, put on the jacket of this is a soldier's jacket, and you can see that you can put it on this one. And now this video shows that. Okay, I'll explain it and then show you what happens. So we are illuminating this piece of cloth with the light first. Okay, and then we turn off the light, and you can see that this, after illumination, this piece of cloth can be used to light a light emitting diode. That LED lamp is here. And now I hope you can see the video. Now you can see this is in real time. So we are illuminating that cloth with the light for a few seconds. Okay, maybe less than a minute or so, we illuminate that fabric with the light. Now the light is turned off completely. The energy stored in that fabric, that it can be used to light this LED lamp. So that is just to demonstrate that with the solar light itself, this fabric can harvest energy. And even after light, or once the light is turned off, the energy stored within the storing device, within that fabric itself, can be used to light this LED. So this is to demonstrate that the wearable devices on this person or soldiers, that can be powered by this piece of cloth, this integrated device. So that work also got so much attention from all over the world. And it was even featured in National Geographic magazine as as an energy harvesting and storing device. So it has a number of applications, as I already mentioned, for military applications, electric vehicles. If you make the roof of an electric car with this type of mat, it can harvest energy and it can store energy, and it can, by the end of the day, if you park it outside in sun, it can harvest energy, store it, and then in the evening you can run another 10 to 15 kilometers or so, which is going to be very beneficial. So I try to convince you that these are some of the energy storage devices, and these are not, the typical energy storage devices. They are in the form of fibers, and we are one of the early groups who demonstrated that these supercapacitors can be made in the form of the fibers, and that can be used for many applications. And we are the first ones to show that this can be used for, these fibers can be used to transmit as well as store energy. And also we have demonstrated that a hybrid device, a energy harvesting and storing device, can be developed by integrating these things, and then make it into a single device, and make a piece of fabric, and that can be used to harvest and store energy. So we have a number of new directions coming up. Unfortunately, I cannot talk about some of those things because we have not published or it is under some classified nature, which I cannot talk about some of those things. But in the hopefully in the near future, I can talk more about those type of interesting directions. And thank you for your attention. And if you have any questions, you can ask me now.
Thank you, sir, for the presentation. Now the seminar is open for discussion. If the participants have any questions, you can directly interact with the professor by unmuting yourself, or you can put it in the chat box also. Sir, I have one question.
Okay, sure.
Sir, what about the perovskite solar cell? Since it is containing lead, how eco-friendly it will be in future, or how can we recycle it?
That's a very good question. I forgot to talk about that limitations. Actually, that is one of the limitations. It has lead. Second limitation is, if you have moisture, if it is exposed to moisture and maybe to oxygen, the degradation of the properties, the conversion efficiency can happen. But there are a number of methods to circumvent that one. To answer to your question, lead, yes, lead is a problem, but there are a number of initiatives to replace lead by tin and other materials, but so far it is not anywhere close to lead, because one reason, the efficiency is not anywhere close to lead, and the second reason is that the stability is also not anywhere close to lead so far. But the one thing is, even if it has lead, the content of lead, as you can see from the structure, is extremely small. Even in the case of silicon solar cell, there is lead, in the circuits and all those things, you have a lot of lead. And in fact, the lead contained in this perovskite solar cell, some people say that it is lower than the total lead contained in the other silicon solar cells and such things. But definitely it is a concern. But there are a number of methods. One, to as I said, circumvent those issues, basically to buy back this perovskite and reprocess it. It is going to be a problem only if you expose it to the environment. If you throw it away and then if it is mixed with the soil and other and the environment, that is going to be a problem. But if it can be, if there are companies that can buy back these things, that is going to be very beneficial, and you can get rid of that problem. That is one method. And also to answer the second one, the problem with the stability, there are a number of encapsulation methods by which you can have a much more stable perovskite solar cell. But still, the stability is not as good as the silicon, not anywhere close to silicon. But if you think about our applications like wearables, you are not going to wear a jacket for 20 years or 30 years like a silicon solar cell. Even if it is stable for 5 years, that would be very beneficial. You don't need to have it for 20 years or 30 years. So those type of applications, this can be useful. But there are a number of companies who makes this type of solar cells for commercial application now, because of it's very cheap. It can be made roll to roll, and it is very flexible.
Sir, and one more question. It's regarding the integrated device, which is a supercapacitor that can also act as solar cell. So what about the heating problem generated there during the storage or during the exposure to sunlight?
We don't see any issue with the heating effect, because unlike lithium-ion batteries, supercapacitors doesn't have that much heating effect. Basically, why it is heating up in lithium-ion batteries? Basically, all these ions are going inside your the electrodes in the case of lithium-ion batteries. But in this case, in the case of supercapacitors, it's mostly on the surface of this electrodes, basically because of the nanostructures. So heating is not at all a problem. But in the integrated device, when the energy is transmitted from the solar cells to the supercapacitors, heating can be due to one, basically because of your resistance, right? That is the reason why it can be heated up to some extent. But here in this case, at least in this case, we use the copper, and in which the resistance is low. So we have seen at least 70% of the energy harvested by 68 or 70% of the energy, if I don't remember it exactly, but that much energy is directly passed on to the supercapacitors.
Okay, sir.
Okay.
Any other questions? You can unmute yourself and ask. Sir, due to curiosity, I want to ask one more question, sir.
Sure, absolutely, no problem.
Sir, recently I had a news from just gone through the news regarding the IBM. So IBM has now just released a news. I don't know whether it is real or not from the website, or I don't note it from the website, but it had from some other video released that they have developed a battery that can last up to 1 year like that. So it can charge in very few minutes. It will be fully charged and it can discharge for 1 year. Maybe they are claiming that a cell phone can be used for the for almost 5 years without charging like that. So what about the reality regarding that? It's
I
from
haven't
IBM.
I haven't seen that report. I do not know. But again, it depends on the energy tapped from that cell, right? For example, for cars and all those things, it needs a lot of energy. But for a cell phone, it requires only very small energy. But still, for 5 years or so, it's a lot. I don't know about it. How that is possible, unless it is a reasonably big battery. And I don't know. Honestly, I don't know. I haven't seen that report.
Sir, in that report, they have means actually it is I haven't seen from their website, but one of the video in I think from one of the science pages regarding that they will provide the science news from everywhere in the world. From that only I have seen, and they have mentioned that they are using a cathode material entirely different from this lithium.
Yeah, but I don't know what material they use. Typically used one is the lithium, and it takes anyway. People have number of car companies. That all these things are going into electric vehicles, right? In another, I believe, in another 20 to 30 years or so, at least 40 to 50, 30 to at least for 30 to 40% of the vehicles are going to be electric vehicles. Here, there is a huge push for that one for electric vehicles, and even my group now we are working with a multinational car company, one of the top 5 for developing some of these energy storage devices. So there is a huge push for this one, and there are a number of reports. I have seen another report in from England also, where this can be charged, the batteries can be charged very quickly, and it can last for several days. But I haven't seen it for 5 years or such things. I don't know, because if it is from IBM, it would have been a big news. I don't know, here at least. And I have seen it. I have not seen it so far in any of the science journals, science news or nature news or anywhere like that. Maybe I missed it. I am not saying that it is not there. I am saying that, okay, I haven't seen it, so I don't know the technology they use.
Oh, okay, sir.
Okay. Any other questions? You can ask me any questions. Don't worry about it. If it is, I typically tell in my class, in my teaching class, I want to hear the silliest question from them. Okay, not the best question, the silliest question. So you should ask these questions. See, I know that many of you guys have so many questions. Only if you ask those questions, then you can learn it. Otherwise, you cannot learn things. So don't be afraid that it is a silly question, so people will think something bad. That is, they are not asking that question because they do not know, or they are not thinking. So please ask me any questions you want, not really related to the subject. If you have any questions about here how it is done, whatever you want to ask in United States, how the education is done, or what, or how we teach, or whatever, you can ask those questions too.
Sir, if you can tell the possibility of higher studies after graduation or post graduation for Indians in US or in university, in your university also.
And that's basically because the graduate classes, as I said before, the masters and the PhDs. Masters, there is no need for GRE. Otherwise, for PhD, I think you need GRE, as well as your GPA. That is the one thing they look at it. Your GPA, your scores for your undergraduate studies as well as graduate studies is based on a number of things. So anyone can apply. They need to make their essays and all those things. For masters, you don't need a GRE score, but for PhD you need a GRE score. That is the difference. But depending on your performance, and there are a number of evaluations and such things they do here, equivalency evaluations and such things, where it is equivalent to American degree or not. That is one thing they always check. And yeah, then admission is typically, we have a number of Indian students, mostly from IITs, and now there are a number of students from ISER, I believe. And we typically get a lot of inquiries from students from those IITs or ISERs and those type of institutions. But you need to explore. That's the thing. You need to explore things. You are curious, you need to write your own essay. Those are the very important aspects. You need to have an essay. You need to write an essay, and that essay is should talk about why you are interested in this degree, and what is your motivation, and all those things. Those type of things, essays are very important here. And also, what is the service you have done there? Voluntary work and such things are very important there. And unlike there, voluntary work is there, it is considered very highly, whether you have done some voluntary work, and how it can contribute to the society, and all those things are important. Your leadership qualities and such things.
Okay, sir.
Okay, if you have any specific questions, you can ask me. And the important thing is that here, as I said before, all this funding, for PhDs and all, the funding comes from PIs. That means process the projects. So we write all the time. We write proposals and submit to the agencies, and they fund it. There are a number of government agencies like National Science Foundation, National Institute of Health, Air Force Research Labs, and all those things. But it is all focused, and the competition is extreme. There is for NSF and all, there is less than 5% of getting one proposal funded. So it's extremely hard. But that's the reason why we need to produce the results too. And we work for companies and all those things. They want results in that those are very strict. So you need to produce the results and show them that whatever they need, we can provide them the research results and all those things.
Okay, sir. Thank you, sir, for the nice, interactive, and informative session.
Sure.
And okay, and I would like to call upon our principal, Dr. Reina Thomas, to deliver the vote of thanks.
In fact, I was not here for some time. some constructions are going on in our campus. So I just want to reach there. Okay. Today we had the fourth session of the international webinar series. I'm glad that all the past sessions were very much beneficial to the academic community. It is fortunate and accidental that we had all the sessions related to advanced materials and the architecture of molecules. Today, we were fortunate enough to hear the advances in nanophotonics from Dr. J.N. Thomas, a senior research scientist of international acclaim. I hope you have seen him in the news in Kerala also. I think it is in the last year, his papers or his inventions, research studies came in the newspaper. So we are very happy and glad that you have given us your precious time to interact with our young researchers and faculty members. So it is we are very happy and grateful to you for accepting our invitation and to deliver the fourth session. So on behalf of all the participants and on behalf of the institution, we express our sincere gratitude and happiness towards you. So Dr. Jain, thank you very much, very happy. I hope everyone have interacted well and about the advances of nanotechnology and its application, wonderful applications. In all the sessions we have been hearing about the advances and the engineering of molecules or architecturing of molecules. So for us, it has been a wonderful experience to hear from you. So thank you, Jay. Thank you.
Thank you for inviting me, and especially I would like to thank your principal for inviting me. We have some personal connections too, which we didn't know. Because my wife and Dr. Reina Thomas, they studied together, and we never knew about it until I received that invitation, and I thought that, okay, this name sounded very familiar to me at that time, and I was thinking, how. And then I talked to my wife, and she said that, oh, okay, I know Reina very well, because I think they did their study, some of their studies MPhil together. So I'm very happy to give this talk, and thanks for your kind words. And if you have any questions, you can contact me. And for any of this, any questions about these things, you can send me an email. You can get my email address online. So thank you very much, and have a great day. So have a great safe day. Hopefully there is some hurricane or something coming. So please stay safe. Thank you.
Thank you. Actually, it gave me an opportunity to refresh my memories with your wife, and I thought I would say that. Okay.
Okay. Thank you.
Thank you.
Bye-bye.
George.
Thank you, sir. And one more instruction to the participants.
Okay.
The next session will be on Saturday, 10:30 a.m. Everybody please join for that session also, because the participation and the feedback form, filling of the feedback form is mandatory for obtaining the e-certificate. Thank you for your cooperation.
Thank you all. See you on Saturday.